In early 2020, prototypes of a new battery electric transport were sent to Alaska. Engineers subjected them to -20-degree temperatures and punishing blizzards to test the durability of a fully electric drivetrain hauling heavy freight. The initial specifications released in 2017 outlined 3 independent motors, capable of accelerating an 80,000-pound load from 0 to 60 miles per hour in exactly 20 seconds. But the pitch that actually caught the attention of the logistics industry relied on long-distance economics. It was the claim of a 500-mile range on a single charge, combined with an estimated operating cost up to 83% cheaper than traditional diesel. Fast forward to 2026, and the narrative has shifted completely. Despite the electric truck finally hitting the road for its first major rollout in the first half of the year, company leadership barely mentioned the vehicle during recent earnings calls. Instead, investor briefings are heavily focused on transitioning the automaker into an artificial intelligence and robotics enterprise, highlighting projects like humanoid robots and autonomous pedal-less passenger cabs. The original manufacturing target was to supply 50,000 electric trucks annually by 2024. Today, only a few hundred have actually been built, and they are mostly restricted to limited local pilot programs. To see why the rollout of this commercial vehicle stalled, we need to bypass the marketing presentations and look directly at the math required to drive a single mile. Moving 80,000 pounds of cargo across the country requires a tremendous amount of energy, especially when pushing a massive box-shaped trailer through the air. To hit the advertised 500-mile range on a single charge, engineers calculated that the truck could consume no more than 1.7 kilowatt-hours of electricity per mile. Data from a 2024 pilot program run by logistics company DHL showed the vehicle consuming 1.72 kilowatt-hours per mile while hauling a combined weight of 75,000 pounds. However, looking closer at the DHL data reveals a significant variable. For more than half of the testing time, the truck was driven at speeds below 50 miles per hour. This chart shows how aerodynamic drag increases exponentially as a vehicle accelerates. At highway speeds, the resistance of the air forces the motors to draw significantly more power from the battery. Because commercial freight networks rely on sustaining speeds of 60 miles per hour on interstates, maintaining that baseline 1.7 kilowatt-hour efficiency becomes physically impossible, steadily eating into the total range. Beyond the vehicle's aerodynamics, a battery electric freight fleet relies entirely on the capacity of the external electrical grid. The manufacturer initially proposed a nationwide system of high-output megachargers powered by independent solar farms. Because this network hasn't been built, early adopters like PepsiCo must install their own chargers and pull electricity directly from their local municipal grids. This graph illustrates the massive shift in power costs. The initial financial models were built on a guaranteed electricity rate of 7 cents per kilowatt-hour. Today, largely due to the insatiable power demands of AI data centers, the national average has spiked to 18.9 cents. Without an independent, solar-powered charging infrastructure to keep rates locked in, the core economic advantage of electric freight, extremely cheap fuel, has effectively evaporated. For a logistics business, fuel is only part of the equation. Every fleet operator has to calculate the amortization, which is the process of gradually writing off the initial cost of a heavy-duty asset over its useful life. A standard new diesel truck costs roughly $150,000. In contrast, the electric semi commands a purchase price of $290,000. Even with national electricity rates nearly tripling since the initial projections, powering an electric truck still works out to roughly 24 cents a mile, which is about half the fuel cost of a comparable diesel engine. This bar chart breaks down the operational math. Financing a $290,000 asset requires monthly payments that equate to about 80 cents per mile, exactly twice the financing burden of a diesel truck. The heavy upfront capital requirements entirely erase the fractional savings gained on electricity, making the electric model significantly more expensive to operate for a standard shipping fleet. Across the vast majority of the United States interstate system, this high-capital, high-electricity cost formula simply does not make mathematical sense for freight carriers. There is exactly one region where these variables invert, making the electric transport highly competitive: the state of California. This equation shows the impact of state intervention. The California government operates the HVIP, the Hybrid and Zero-Emission Truck and Bus Voucher Incentive Project, which hands buyers a massive $120,000 subsidy to offset the purchase of a zero-emission truck. At the same time, localized state taxes push the price of diesel fuel roughly $1 per gallon higher than the national average, widening the comparative savings gap for EV operators. The manufacturer recently built a factory with the capacity to produce 50,000 of these trucks a year, yet the entire state of California only purchases about 30,000 new heavy trucks annually, across all brands combined. By confining its viable market to a single, highly regulated state, the vehicle functions as a subsidized niche product rather than a wide-scale replacement for the combustion engine. Regardless of the battery technology or the aerodynamic engineering, a commercial vehicle must ultimately conform to baseline economics.